Well, welcome back, folks. Today, our focus is going to continue on unit number 1, our focus mostly on atomic structure and electron configurations. Now, we're going to start off fairly basic with just the basic structure of an atom and how that works, and we're going to dive into some electron configurations, hopefully some things that you're already aware of, but then we're going to take those concepts, relate them to what is known as Coulomb's law to be able to explain a variety of different periodic trends that you find present on the periodic table. Very excited to have you with me today. Let's go ahead and dive right in. So hopefully by the end of this video, you should be able to explain the subatomic particle structure of an atom, understand how Coulomb's law is used to define the force between particles, write out full electron configurations, differentiate between inner core electrons and outer valence electrons, explain the relationship between ionization energy, atomic radius, and Coulomb's law, and analyze a photoelectron spectroscopy diagram to determine the element based on the number of peaks and peak size. So we got a lot going on today. Let's go ahead and dive in. So let's start off by talking a little bit about the atomic structure. And as you are probably aware of, atoms are composed of 3 primary subatomic particles, that being protons, neutrons, and electrons. Protons are positively charged, electrons are negatively charged, and the neutrons have no charge. Protons and neutrons are exclusively found within the nucleus, and electrons exist in 3-dimensional regions around the nucleus called orbitals. Don't confuse that with them just orbiting in circles around the nucleus. Now, we're not going to go into too much modern atomic theory here, but just understand that those electrons exist in those 3-dimensional regions. We can go back and talk about Heisenberg uncertainty principle, and that we can know, the more we know about the location of an electron, the less we know about its momentum and vice versa, but for our purposes, we just need to know that they exist in these 3-dimensional regions known as orbitals. Now, electrons exist in shells and sublevels. Those shells are also known as the energy level. Higher energy levels indicate that those electrons are further from the nucleus. You can just think of them, being further away, having more energy as they are further away from the nucleus. Now, we can describe the location of these electrons roughly using what is known as an electron configuration. So how do we go through and determine electron configurations? Well, electron configurations are based off of a variety of different factors, and the best way to take a look at this is to kind of break down the periodic table into a series of letters and numbers that are based on the location of the element on the periodic table. So what we're going to look at here is your energy level, the first thing we're going to look at. And that's typically given as the period number on the periodic table. So you see the first period going across that just contains hydrogen and helium is known as the first energy level. The second period going across is the second energy level with lithium, beryllium, boron, etc. The third energy level containing sodium, magnesium, and aluminum is the third energy level, and so on. We also have blocks of elements, and this is more known as your sublevel. So we have our S block, which is groups 1 and 2 on the periodic table. These are fairly easy to recognize because the heights of each of these groups or these blocks are different from one another. So groups 1 and 2 are known as our S block. Groups 13 through 18 are known as our P block. Groups 3 through 12 is known as our D block, and then our lanthanides and actinides are known as our F block elements. So kind of using this as like a grid, we can determine roughly the locations of those electrons, or at least be able to describe specific electrons as well as which sublevel that they are in. So as we go through and write out our electron configurations, we're really looking for 3 things. We need to write out the energy level, the sublevel, and how many electrons are in that sublevel. Now, the maximum number of electrons in a sublevel is dictated by how many elements wide the sublevel is. Now, there's a bit more complex way to look at this as well. But what we're going to look at here is that the S is 2 groups wide, so it can hold a maximum of 2 electrons. The P sublevel is 6 groups wide, so it can hold a maximum of 6. D is 10, and F is 14. Now, that's based on the idea that there are orbitals in which these electrons rest, and there are a maximum of 2 electrons that can be held within each orbital. So the S block is 1 orbital with a maximum of 2 electrons. P has 3 orbitals, which is a maximum of 6. D has 5 orbitals, which is a maximum of 10. And F has 7 levels, which is a maximum of 14. So if I want to write the electron configuration for hydrogen, I need to write out the energy level, which is 1. I need to write out the sublevel, which is S, and it is in the first group of the S block, so it has one electron in it. So its electron configuration would be written as 1s1. Helium, on the other hand, is in that second group. I know it looks like it's all the way off there on group 18, but notice it's highlighted in red. We do include helium with our S block. So it is in the first group, it is in the S sublevel, and because it has 2 electrons in it, we would describe that as 1s2. If an element is beyond a sublevel, we assume that it is full. So as a result, if we look at something like sodium, which is in the 3s block, we would assume that all of the orbitals before it are completely full. So we would write that electron configuration as 1s2, 2s2, 2p6, because again, p can hold a maximum of 6 electrons, and 3s1. A very easy way to determine if you got this correctly is to count up the total number of electrons you've allocated, and if the atom is neutral, it should equal the number of electrons that are in that structure. So for example, sodium, a neutral atom of sodium, has 11 electrons. So it will have 11 electrons in its electron configuration. 2 plus 2 plus 6 plus 1 is 11. Now, this gets a little bit trickier with the D block and the F block. The D block has 10 electrons in it, and as a result, that means that those electrons are more closely attracted to the nucleus. So even though the first D block occurs in the 4th period of the periodic table, or the 4th energy level, we actually subtract 1 from the energy level. So that first group of D block elements is actually 3D, not 4D. And with F, we actually subtract 2 from that. So for example, if I want to give the electron configuration for bromine, well, remember that all of the previous sublevels prior to bromine are full. So we start off with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Then remember, with the D block, we have to subtract 1 from the energy level. So that is going to be 3d10, and then 4p5. That gives us our electron configuration for bromine. So again, just quite a few things to keep in mind here. Hopefully you've gone through and done electron configurations before, so this is just a little bit of a review. But just again, make sure you keep all of these rules in mind as you go through and complete electron configurations. Ions need to be represented with additional or fewer electrons based upon its charge. So remember, if we have a positive charge, that means that an atom has lost an electron, and if we have a negative charge, that means that the atom has gained an electron. So we need to make sure to write our electron configurations according to that particular rule. So remember that sodium, elemental sodium, is 1s2, 2s2, 2p6, 3s1. Well, Na with a positive charge means that it has lost an electron. We do need to keep in mind that atoms are going to lose the outermost electron before losing any inner electrons. So the outermost electron, the one that is furthest from the nucleus, is going to be the one in the 3s sublevel. So as a result, we're going to lose that electron, so our new electron configuration is just simply going to be 1s2, 2s2, 2p6. This is in addition to gaining an electron. We're going to gain an electron in the outermost sublevel. And so as a result, you need to just kind of keep those things in mind as you go through and look at ions. Electrons in an excited state don't normally follow the pattern. So a normal state for sodium would be 1s2, 2s2, 2p6, 3s1. An excited state of sodium would be 1s2, 2s2, 2p6, 3p1. Notice how it completely jumps the 3s sublevel into 3p1. So if it doesn't follow the normal order of electron configurations, that tells you that that atom is in an excited state. Noble gas notation can be used to abbreviate the electron configurations. We simply just replace the electron configuration of the last noble gas we passed. So again, we go back to sodium and find that sodium is number 11 on the periodic table. The last noble gas we looked at is neon, as we went through and have written our electron configuration. So our normal state is going to be 1s2, 2s2, 2p6, 3s1. What we would do is just write our noble gas in brackets, and that represents the electron configuration up until you get to that noble gas. So if we're looking to write the noble gas notation of sodium, I'm just going to place neon in brackets and then just write 3s1 after it. So hopefully electron configurations aren't going to cause you too much trouble. One other thing I would keep in mind is that when we're looking at things that have D block elements in them, that you really want to make sure that, for example, if you have something that's 4s2 3d10, and let's say it's an ion, it is going to lose those 4s electrons prior to losing the 3d electrons, because remember that those 4s electrons are not core electrons. They're further away from the nucleus than the 3d electrons are. So that's one thing that's a little bit tricky that some students tend to make some simple errors on. So let's switch on to a different topic here and talk a little bit about Coulomb's law. And for you students that are taking AP Chemistry, it is absolutely imperative that you understand the concept of Coulomb's law, because this is going to describe a lot about atomic structure. And you're going to have a lot of questions that are based off of Coulomb's law. So the better you understand this concept, the more a lot of periodic trends and things like that are going to make sense. Coulomb's law simply states that the force of attraction between charged particles is directly related to two things. We need to keep in mind that like charges are going to repel one another and opposite charges attract. Very simple, just like you would describe with a magnet. The two factors that play a role in Coulomb's law are the magnitude of the charge. That is, if we have greater charges, they are going to attract each other more than things that have smaller charges, just like stronger magnets are going to attract each other more than weaker magnets would. In addition to that, the distance between the charges. So, for example, magnets that are closer together are going to have a greater attraction than magnets that are further apart from each other. If we can keep in mind those two concepts, we can explain a lot about the different trends that exist on the periodic table. Furthermore, I'm also going to use a term that is known as nuclear charge, and nuclear charge just basically describes the attraction of the electrons to the nucleus. There's a little more detail into that I'm not going to go into at this point, but if we keep in mind the concept of nuclear charge as just being how attracted those electrons are to the nucleus, we can make some really good observations about different trends that exist on the periodic table. So let's differentiate between the concept of core or inner electrons versus outer or valence electrons. Inner electrons are called core electrons, and they're very, very, very difficult to remove. The reason being is that those electrons are very, very close to the nucleus, or at least closer to the nucleus than outer electrons would be. Because those electrons are closer to the nucleus, they experience greater nuclear charge, therefore they are more attracted to the nucleus because they are closer to the nucleus. Remember that the nucleus is positively charged and the electrons are negatively charged. And so because they experience greater attraction, they're very, very difficult to remove, or at least more difficult to remove than the outermost electrons. Now, outer electrons are much easier to remove for a variety of reasons. First off, they're further away from the nucleus, and so as a result, they're going to experience less attraction to the nucleus and therefore are going to be much more easier to remove. And then secondly, they experience less nuclear charge because A, they're further away from the nucleus, and B, the innermost electrons shield that positive charge from reaching out to those valence electrons, thus making them easier to remove. The ease of the removal of an electron is based on nuclear charge and Coulomb's law. So if we think about those two concepts, we can easily determine which electrons are going to be easier to remove and which electrons are going to be more difficult to remove. On the right-hand side here, you see silicon. The inner core electrons are your 1s2, 2s2, 2p6 electrons, but 3s2 and 3p2 are easier to remove because they are the outermost electrons. In addition, if we look at germanium, the 4s2 and 4p2 electrons are going to be the most difficult to remove. The inner or core electrons include 1s2, 2s2, 2p6, 3s2, 3p6, as well as 3d10. Keep in mind, 3d10, those electrons are closer to the nucleus than 4s or 4p are. Again, electrons that are further from the nucleus experience less nuclear charge, again, for two reasons. That results in less attraction to the nucleus due to their distance from the nucleus, as well as a concept known as nuclear shielding, meaning that those other core electrons reduce the amount of positive charge attraction that those outermost electrons receive. As a result, this makes the outermost electrons much easier to remove than those inner core electrons. So let's think about this. Which is more likely to lose an electron, sodium or potassium? And justify your answer. Well, if I look at the electron structure of sodium and potassium, both of them have very similar electron configurations in that they have one electron in their outermost s orbital. But we have to think in terms of Coulomb's law. The potassium lone electron in the s orbital is further away from the nucleus than sodium's lone electron is. So as a result, potassium is your answer, because the outermost electron of potassium is less attracted to the nucleus as it's further away from the nucleus than the outermost electron of sodium. Because it's less attracted to the nucleus, the electron would require less energy to remove. So again, this goes down to The electron experiences less nuclear charge due to nuclear shielding, as well as it being further away from the nucleus. So again, lots of things to kind of keep in mind here, but all of it makes sense if you think about things in terms of Coulomb's law. So what about atoms that are in the same energy level? How do we compare them in terms of the amount of energy required to remove an electron? Well, in the same energy level, the amount of energy required to remove an electron increases. As we go across a period on the periodic table, the number of protons increases, right? As we go across a period, so let's say that third period, we start at 11, and then we have 12 protons, 13 protons, 14 protons, 15 protons. Well, as the number of protons increases in the nucleus, that increases that positive charge that is in the nucleus. As the positive charge increases, that means that those outermost electrons are going to be more attracted to the nucleus because the magnitude of the positive charge of the nucleus continues to increase. That means that it requires more energy to remove an electron as we go across a period on a periodic table. This is due to increasing nuclear charge. That positively charged nucleus becomes more positive as we add more protons. As a result, the outermost shell of electrons gets smaller and gets closer to the nucleus, thus making those electrons harder to remove. So again, if we think about things in terms of Coulomb's law, magnitude of the charge and how close those electrons get to the nucleus, we can make sense of the fact that ionization energy, or the amount of energy required to remove an electron, increases as we go from left to right across a period on the periodic table. So let's again shift gears here and talk a little bit about photoelectron spectroscopy. Now, this is very much a simplified version of it, as we can do this for a variety of different ions and atoms and even compounds. But photoelectron spectroscopy is essentially the energies of the electrons that are observed in a chart here. And so as you see on the right-hand side here, we have a chart that shows the relative number of electrons and the ionization energy. The peaks correspond to each sublevel and the number of electrons. So as you notice, on the far left-hand side here, we have the greatest ionization energy, which means that those peaks represent sublevels that are closer to the nucleus. So we would be able to label that very first peak on the left-hand side our 1s sublevel. And then the next peak would be 2s, then 2p, then 3s, then 3p, etc. The peaks then correspond to the number of electrons as well. So you notice we have sublevels that are far beyond the 1s, so I could say that that very first peak has 2 electrons, which would make sense because of 1s2. Then 2 electrons in your 2s, and then 2p, you notice it's about 3 times as high as the 2s, so we can assume that it has 6 electrons in it, which would make sense because it is a 2p sublevel, and so on. So again, if we look at these electron configurations, we can determine the element that's present and determine lots of different factors about those peaks as well. So let's think about this. What element is being represented here? Well, we have a 1s sublevel, and then 2s, 2p6, 3s2, 3p6. So I would argue that this is a photoelectron spectroscopy of argon. Because if I look at this, I can easily determine the electron configuration from it. 1s2, 2s2, 2p6, 3s2, 3p6. So the peak location when comparing elements or ions needs to have Coulomb's law taken into consideration. So if I look at the difference here between phosphorus and sulfur, and what I notice is that the peaks are very similar. I notice that the 1s peak for sulfur is actually closer or has a higher ionization energy than the 1s peak for phosphorus. I also notice that the peak for the E peak on the far right-hand side is smaller in phosphorus than it is in sulfur. So let's ask a couple questions here. What sublevel does peak A represent in both elements? So peak A, you notice it has the highest ionization energy, so we can assume that it is the sublevel that is closest to the nucleus. So we're going to assume that peak A is going to be our 1s sublevel, again because it's closest to the nucleus, has the highest ionization energy. Why is the ionization energy of peak A greater in that than sulfur than in phosphorus? Well, if we take a look at the periodic table, sulfur and phosphorus are on the same energy level. And so as a result, what I notice is that sulfur is further to the right in the group than phosphorus is. So sulfur has 1 more proton in its nucleus than phosphorus does. So the electrons in sulfur are going to experience greater attraction to the nucleus because there is a greater nuclear charge in the nucleus of sulfur than there is in phosphorus. So First off, we're going to describe A as the 1s sublevel, just like what we talked about. But sulfur has a greater nuclear charge than phosphorus due to there being more protons in the nucleus. This results in greater attraction of the 1s electrons in sulfur and makes them harder to remove, thus a higher ionization energy. So again, if we go through, take a look, count up the number of protons, we can understand that sulfur's energy levels are going to experience a greater nuclear charge than phosphorus is because of the greater number of protons in the nucleus of sulfur than phosphorus. And as a result, we can then take Coulomb's law into consideration and understand why it would be harder to remove a 1s electron in sulfur, thus having a higher ionization energy. So there's a lot going on in this. But again, what I want you to understand, what I want you to think about is everything in terms of Coulomb's law. The number of protons in the nucleus matters in terms of the ionization energy and how easy it is to remove a valence electron. We also need to keep in mind the concept of core electrons versus valence electrons and understand how that directly correlates to writing all of those electron configurations. So lots of things to think about in terms of this, but take your time. We'll go through it in class, and hopefully you'll have a better understanding as we continue to go through and dive into the material. Hope this makes a little bit more sense to you guys. Have a great day, and we will see you soon. Bye-bye.